We shall start. Let me introduce myself. I'm Ksenia Bolesnikova, and we with Konstantin Stepovoi made work about which I'm going to tell you now. Propagation of electrical impulses along nerve fibers. We owe almost all our life to electricity in our bodies. Thanks to the electrogenic properties of living tissues, we receive information about the external world and control ourselves. We will be interested in our work in such a characteristic of a nerve fiber as action potential. Why is it interesting? This is the value of the potential difference in both sides of fiber membrane, starting from which there is a change in fiber's properties. At rest, potential difference is maintained at the border on the membrane between the cytosol and the extracellular fluid. The inner part is negatively charged and the outer part is positively. This is regulated by modes of ion transport across the membrane. Local changed potential difference spreads from the place of origin in both directions with attenuation from the distance. Here we can see the cable equation, which describes this fact. But the membrane functions like this exactly until stimulating our local change potential difference evoke action potential. In order to obtain action potential, it is necessary to observe the correspondence of the amplitude of the supplied pulse and its duration. The asymptotic approximation of this hyperbola to the time axis indicates the existence of the Rhea base. Rhea base is a threshold force. If we supply a pulse with an amplitude less than the Rhea base, then, regardless of its duration, the action potential will not arise. Chronoxy, we have the second parameter is chronoxy. It's the time during which an impulse equal to a double Rhea base in its amplitude must act to trigger an action potential. This value can be compared with tabular values. The action potential consists of a cycle of membrane depolarization, repolarization, hyperpolarization, and returning to the resting value. If the signal is not sufficient for the appearance of the action potential, such a large amplitude will not be observed, and there will also be no hyperpolarization section here. Next slide contains photo of nerves, so get ready. It would be one, but it would be, yeah. What experimental setup we use? Inert electrode, inert platinum electrodes were inserted into the nerve. DAC allow applying the voltage needed amplitude, and ADC remove the signal with the required gain. The values we interested in are quite small and sensitive to external conditions, so we also use metal shell. Moving to results, we were able to determine the value of the action potential, so the moment at which the dependence changed its character. Here we can see for voltage that are less than necessary to get action potential for one duration. Swapping the electrodes in places, we checked the law of bilateral conductivity. You can see both action potentials for the frog, for the same frog, red and green one, but one of them get from left to right electrode, and the second one after replacing them, and they're quite equal. We made experiments on spar frogs and Ahatin snails, and the fact that the recorded signal is almost identical confirms the properties of the mixed nerve fiber. So yellow is for snail. And time parameters correspond to the accepted one. Once you can see theoretical values colored gray. What about depends of the strength of the incoming signal on its duration at the value of action potential? It also differs little in the snail and frog, as we can see here, as both animals belongs to cold-blooded. So the values of Rhea base and chronoxy of the nerve fiber were obtained, and they fall within the range of theoretical values within the margin of errors. Moving to next parameter of action potential, to velocity of potential propagation, we can calculate it using some parameters which we can get from knowing what is time and length constants. So what is it? Time constant is a handy indicator of how fast exponential functions change over time. And in our experiment, it is a function of the membrane resistance and membrane capacitance. There is also an index like a length constant, which indicates how far the potential will propagate along the axon in response to subthreshold stimulus at another point. In our experiment, again, it depends on diameter of the axon, again, membrane resistance that we had, and new parameter is exoplasm resistance. So having experimentally obtained time and length constants, it's possible to calculate the speed of propagation as we did. So, but also the speed of propagation of the signal was determined by another method, by measuring the distance and time for which it was passed. So comparative data for both methods and theory are presented on this slide. Values are close to theoretical, and methods are comparable in accuracy, but in the method through constants, a large contribution is made by the methodological error. And in the method for determining this speed, the accuracy of direct measurement